the catacomb group is like allowed to go back to her daycare faster than my daughter who'd been exposed to something.
What are they doing? No. Oh, you got
Hey, Colin.
It's funny, just after I left you, said, do you know the Wesley from
Wesley had been my postdoc.
well, he was I was on his team.
I didn't know that. Wow.
Maybe it was Diane. I was on one of those, at first.
That's wild. It's funny, he never mentioned that.
Yeah. All right, let's get started. Before we see our speaker today, we remind you of the events next week. We have 2 talks at 12:10, noon 10 on Tuesday and Friday. Again, Fisher will be talking on Tuesday about experimental argument analysis, how stereotypes shape argument. And on Friday at 12:10 again, John Norton will be talking about analogy and thermodynamics. So you're invited for these 2 talks. If you want or must attend one of these talks online, remember you can register on the website by going to your calendar and you can have access to the Zoom link, getting an invitation for Zoom. Today, it's my great pleasure to introduce Rob Pennock, who is spending the semester or last part of the semester with us at Pitt. So if you didn't know and want to meet Rob, I'm sure Rob would be delighted to actually meet with you, spend some time with you, talk to you. So don't be shy, send at the end of the talk, come and introduce yourself or send him an email. I think that we would be delighted to do that. Many of you know Rob, so I'll keep my introduction short. He's a university distinguished professor at Michigan State University in both the Department of Philosophy and the Computer Science and Engineering Department of Lehman Briggs College. So he didn't know he got his PhD here at Pitt in the Department of History. Well, I didn't know.
How could that be?
A lot of things I don't know. In 1991, you might know him from various areas because his work actually on a lot of different topics and issues related to evolution and creationism is actually quite famous for his contribution to the Kitzmiller versus Dover Area School Board trial. I do actually remember that. It was my first years in the US, in fact.
Welcome to America.
An introduction to the United States of America. Oh my God, what did I do to myself? And I actually do remember you being very much involved in that quite shocking bit of, we won't forget the quite shocking bit of American history. And that led actually to quite a great book called Tower of Babel, the Evidence Against the New Creationism, which I think quite a successful book, and that was nominated for the Pulitzer Prize when it was released. Rob has won many awards for many societies and so on and so forth, such as the American Association for the Advancement of Science, the National Association of National Academies of Science. His most recent book, if I'm not making a mistake, correct me if I'm wrong, is actually a book I had read, An Instinct for Truth, Curiosity, and Moral Structure of Science. It's a great book. And I actually, if you're curious, I really recommend it. Personal recommendation. Today, Rob's going to talk about curiosity systematized, the philosophy of science, and the philosophy of mathematics.
Thank you, Edward, and thank you all for coming. And for me, it is a coming back. I guess I was here 6 years ago with an invited talk and gave a very particular, formal, regular talk. But this time I thought just because of the occasion, I would not give the normal sort of argument, very focused, that I would give a 10,000 view talk of projects that I've done, because I realized I couldn't talk about any of them. The book that I'm working on now, I thought, oh, maybe I'll give you an outline of that. But I thought even that is going to be a little too hard. So what I'm going to do is give you a bunch of projects to sort of show how they hang together, with the idea that they could stimulate conversation. I do hope that while I'm here, I can chat with people. And I thought this would be a way of showing lots of possible topics of conversation. My initial plan was to really focus very specifically on some debts that I wanted to pay back from my time here as a graduate student and the various professors that I had who inspired me and in a way were roots for much of what I've done here. In my seminar that I took with Adolf Grunbaum, he would always spend pretty much the first third of every class saying what it was he was going to do in that class. And you could pretty much predict that then the next 2/3 of the class would repeat and expand upon that. And I'm not going to take that long, but I do want to give a little bit of an introduction to these folks that I wanted to thank. My thought had been that I would sort of go through and show the roots of what I'm doing now in these particular three philosophers that were here and that I studied with. Wesley Salmon was my dissertation director, and really his work is what drove me to look specifically at causation, not just an explanation, but really my dissertation was thinking about how one could move that into confirmation. So specifically taking an ontic view of inference to the best explanation, and now thinking about this in a way that seemed to me was a parallel notion to give an idea of what I called evidential relevance, that the relevance relation really was a causal relation. And what I did was sort of give an analysis of how to think about that causal relation in a way so that you had the pragmatic factors of picking out the item of interest and showing how this worked with regard to controlled experimentation, confirmation generally, but also then how it could help resolve some of the typical paradoxes of confirmation by bringing in this relevance relationship and so on. But really the idea was, hey, it's okay to talk about causes. And not only that, it's a valuable thing to do. And it's also a way of getting in this idea of relevance and evidence. So that was kind of a key thing. With Sellars, of course, the idea was trying to think about how it is that what we do as knowers can be understood in relationship to the scientific image in connection to the manifest image. And I learned my Sellars actually first from Bob Brandom, who I took my epistemology course with here. So I got the left-wing Sellarsian view. I found myself more on the right-wing Sellarsian camp, but really stimulated so much from Brandom's view. But the course I took with Sellars himself was his course on Kant. And what I really got from that was sort of the challenge of how to think about this idea of knowing and justification, right, in relationship to how it is that we conceive of ourselves as knowers. And again, sort of my take on this was to try to see how perhaps we could do this in relationship to truly an ontic view without falling into the trap of a simple reduction and a naturalistic fallacy of that sort. And it seemed to me as though that there was at least an opening on that side to do that sort of thing, but definitely an interesting challenge from that. So when I was sitting in, I'm going to tell at least a couple of stories of people. When I was sitting in Sellars' class on this, which down in one of the nationality classrooms downstairs, and the windows were open. They're talking about Kant and how it is that we are able to have knowledge and so on. And as I was sitting there, one of those little birds that nest in the cathedral, in this case, a little yellow one, flew through the window and flew around the room for a while and then landed right on my desk in the middle of class and really disrupted everything, but really was sort of important of my thought about how it is that we ought to be thinking about this, which is not really just in terms of ourselves as human knowers, but in terms of knowers of animals as well. And really my work then and subsequently has been thinking upon how it is that we address Sellars' challenges and so on with this idea of how not we are just knowers now, but how we and anything comes to be knowers. And then that takes me to Simon, who is on my dissertation committee here as well. And there, I was thinking how it is that we come to know about the world in a way that we could model and test in computer systems. Simon, of course, was focused on this in a way of thinking about cognition as computation. Well and good. He certainly understood and appreciated that we would have to have an evolutionary account, but that was not really his focus. And the way that he thought about this was really in terms of symbol manipulation. But my interest then was to take this from that realm into a realm where we could think about it in a true evolutionary context. And I'm going to show a little bit about some of the work that I've done in doing modeling of that sort. Here's my one general statement that's going to give an overarching view of this, that Athena did not spring full formed from the forehead of Zeus, and neither did her owl. So really my work has been to try to explain what it would mean to how it is that we come to be knowers. It certainly didn't come in a godlike way. It did not come supernaturally. Edward mentioned my early work with the creationists. That was really an intelligent design group that was pretty sophisticated in relationship to their critique on this, and included Alvin Plantinga as one of their advocates. And I remember my discussion debate at the APA with him, specifically about this idea of what would be a warrant for knowledge. And if you go into the details of his position, it's very much a design-based position with a supernatural element of God's grace that really is not eliminable from the position. And of course, it seems to me as though if we're going to take a scientific approach, and part of what that book was about was showing that that involves a methodological naturalism, right? That this would be the way in which one would have to do it. And again, my argument would be that evolution, in fact, does provide a way to not only think about that, but to address that issue. And if you don't think of it in that way, really we're only doing epistemology at the very end of the story, rather than thinking about it from the beginning. Okay. And my claim would be, this ought to be true in the way we think about epistemology, broadly speaking, right? That you need to account for how we got here. It didn't just arise all at once. Okay? So that's going to be a general thing. It's not just didn't arise supernaturally, but in fact, I think we should think of this broadly. Sellars himself says that the manifest image is sort of the last refuge of special creation, and I think that's something where it's obviously not meant in the way of the special creation of the sort that the true supernaturalists come to, but I think there's something very similar, and that epistemology really just hadn't really grasped and come to terms with this idea that we have to try to get past that sort of notion. So that's what my overarching goal has tried to be, to rethink of science in terms that could account for how it could come to be, with science, on my view, as being our best way so far of coming to know something about the world. But again, that didn't arise full blown out of the head of Zeus. It itself would have been something that arose out of prototypical ways of knowing before we were theorizers, right? Before we were language speakers, before perhaps we were even recognizable as animals. And the question is going to be, how far down do you go? The key part that I want to be interested in is philosophy of science and thinking about that as a structure where it needs to have a story to be able to give the biological roots of what it is that we now do beyond biology, but as philosophers. And so this is my two-word way of thinking about it, that what philosophy of science does is provide sort of a normative reconstruction. So it's providing an idea of how it is that we ought to act, right? How we ought to behave, how we ought to be as scientists, so that we come to know in a justified way, in a warranted way, about the world. And I'm rooting this at the level of initially biological curiosity. It's not the only kind of knowing, but it's what I think of as one of the virtues that is the basis for coming to know about the world. And out of that biological basis, we as scientists then try to systematize it. And of course, we as philosophers, and I think the job of philosophy of science, right, is to do that in a systematic way. And to me, this is the thing that's incumbent upon us, right, to meet Sellars' challenge, right? We're going to have to find some way to have organisms which are not scientists, but which do come to know about the world, so that you can figure out how it is you get from there to here, and then what it is that we ought to do in order to be better as scientists, both in our methods, but also I would say in the way that we think, in our dispositions and in our virtues. So that's the overall idea of a virtue philosophy of science, right? So that we don't just focus on what's near and dear to our heart, which are the concepts, the theories, the methodologies, the logic, right? All of that we love, but it seems to me that we haven't paid enough attention to something about the nature of the scientist rather than just the things of the scientist, okay? And it seems to me as though a virtue approach rooted in this type of way is a good way to explore that in a way that can connect those two realms. That's the idea. And I'm going to do it through Darwin. And I like to use this line, a couple of lines from Darwin's correspondence, where he's reflecting upon his own internal feeling as a scientist. He says, like, I just believe there exists and I feel within me an instinct for truth or knowledge or discovery. Instinct for truth, obviously, is the reason for the cover title of my book, right? Of something of the same nature as the instinct of virtue. And our having such an instinct is reason enough for scientific researches without any practical results ever ensuing from them. Now, he's not saying that it's a bad thing to have practical results, right? That's okay, but it's that we don't need to have that. It's valuable enough, in part because it satisfies this really deep motivation, disposition to know, okay? That's reason enough, right? So I'm going to go through some of the elements of this, but here I'm just going to focus briefly on the truth, knowledge, and discovery. So here's very briefly some of the things. So the truth he's talking about is obviously not Zeus's truth. It's not God's truth, right? It's, as I argue, true enough, okay? And this, of course, is my element coming from Simon, the idea of satisficing, and the idea of recognizing that we have bounded rationality and that our approach to this has got to be something that recognizes that. So I'm going to have a notion of truth that's going to be analog rather than just all or nothing. The kind of knowledge here is not just propositional knowledge, that it's got to be something that accounts for the knowledge that one has before one is a language user. Before you even get to that realm, you've got to know at least knowing how. I think you also need to account for knowing what, knowing of, knowing why, knowing. There are a bunch of other knowings that you need to have. Knowing how is a key one because that involves actions and so on. And again, for Sellars, that's going to be important role, actions turn out to be the place where you have a normative connection. And again, I think of this as incumbent upon us to think of how it is you get to the theorizing later, but what it's built upon. And then discovery, this idea of actually uncovering something about the world, revealing things about it. And here I'm going to just focus for the moment on this idea of understanding, revealing the reason or reasons why, which of course is my then connection to Salmon and this idea of explanations, right? What you're doing in making a discovery is revealing the explanation, revealing the reason why. And again, I think an ontic causal notion of reason here is a good way to go. I think that's a way to connect what Sellars was after with the ontic approach that Salmon had. Darwin talks about this in terms of an instinct for truth, okay? So he thinks that this is something that is biological. Now, again, I don't think that it's full-blown science, obviously not, but the idea is that there's something that we're evolved to be able to do. We evolve dispositions that allow us to figure out our world, okay? There are going to be reasons you need to do that. And there are reasons why that would be selectively advantageous. Okay. So there is just a bunch of curious animals, right? I'm not going to go through the argument of why it is at the moment that you would need that type of, or why that would be a useful thing to have, that type of ability. But very briefly, the idea would be that depending upon the structure of the world that you find yourself in, there are going to be certain things that in order to survive and reproduce, you better figure out, right? Certain things you're going to be able to figure out over generational time, if the structure of the world is such that it allows regularity at that level of granularity. Other types of regularities in the world are going to be tighter. You're going to have to wait until you come into the world to figure out what that is, okay? That's then going to require learning, okay? And learning is not going to be something that you do unless you've got the dispositions there to seek out, figure things out. And I would say, you know, that's what curiosity is doing, right? It's that disposition to figure out the regularities that are intra-life regularities that couldn't have just been hardwired in, okay? So different kinds of worlds will have different kinds of needs for this and different balances, but overall, that's the kind of structure that promotes the selective advantage of that sort of disposition. Right? So now I'm going to start talking about some of my projects. So that's the basis of what's been a long-term project, really. This started probably 25 years ago, specifically trying to do modeling, not from a top-down approach, which is typically the way AI has been done, right? Let's figure out how we think and try to do something that implements that in a computer. Obviously, there are a whole range of things that ways in which that's done. Simon's early work was on logic theorist, right, as a way to doing automatic discovery, so on. When I was here, there was work that was being done to do AI with regard to medical diagnosis. Caduceus was being done at that point in time. All of that's great stuff. I do some of that all along. But again, my key interest is to say, let's not just think about building it from top down, but rather think about how it is that you could model a bottom-up approach, right? So my move in this was to move from an AI to an EI. So the EI project is evolving intelligence, and to ask how it is that an evolutionary mechanism could evolve the components, obviously not all at once full-blown knowledge ability, but the components that make for knowers, that make for intelligent behavior and so on. And then to do a system that would allow you to model and experimentally investigate that. So after doing that for a while, we were able to get some major funding for a center which specifically looked into this in a broad way. So our Beacon Center is for the study of evolution in action, NSF Science and Technology Center. Basically, it has a number of areas, but all of them have to do with being able to investigate evolution in action as it happens, right? Not just looking into the past and figure out something about that, but in operation. So we're really mostly interested in the dynamics of the mechanism. So the logo here sort of depicts our approach, which is to say that we can do this now in this combined way of looking at natural organisms and the evolution of their own genomes and their behaviors and so on. But we can also now do this in digital systems, okay? And here now we have the other part of the helix with the bits and so on. And the model systems that we develop were ones where you can have evolutionary processes implemented in the computer. And actually, when I talked about this 6 years ago when I came, that was the formal paper that I gave, essentially showing why it is that if you understand the way models work and the way this model works, you should think of this as not a simulation of the evolutionary process, but really an instance of it. And I sort of talked about the difference between simulation models, instantiation models, and how it is that we're able to now actually implement an instance of the evolutionary process, which then lets you do experimental evolution. So that's what we do at Beacon. We take a look at natural organisms in relationship to digital organisms and play each off the other, okay? Asking questions about things in some regular model system, but then implementing some computational models of it to be able to sort of test it in a way that you can't do or can't do as easily in the natural system. Very briefly, here's the overview of this, right? The thing that evolves is code, okay? And the code could be in DNA or RNA, but of course, Darwin didn't know the basis of it, doesn't matter. Okay, this is what Dennett says as the idea of substrate neutrality of the evolutionary process. What we do is essentially implement this in computer code. And on the right is a representation of the computer code of what we call an Ovidian, sort of an A-life form. This is from the way we depict it in the Avida Ed version that I developed with my group. And I'll show you that working in a moment. But the idea is you're going to have random variations that occur, random mutations that occur in the code. It has to self-replicate. Okay, so you have inheritance of whatever those are. And then the organisms compete with each other in a virtual environment where they get rewarded based upon what they do, which then provides natural selection. So you get all the elements there so that the code itself can evolve. So here's just a depiction of a replication event. Okay, each of the dots on the screen represents a single instruction. Combinations of instructions are needed to do things. These are sort of at the level of assembly language kinds of things. This is represented in such a way so that you can see the execution of the code. If things are reused, the arcs, which represent the path of execution, go up. So it shows you've gone back and used that again. You saw the replication event, right? The daughter cell budding off. And if you compare on the right, you'll see some of those are different in a few spots. The N, M, and Q. These were random mutations that occurred in the code. There you had the origin of variation. And then if this replicates, of course, those would be inherited. Okay. Each of these organisms resides in a population. And so what you see on the right is our virtual Petri dish. Each one of those squares represents one organism, which is doing just what I showed you. And basically then in that virtual environment, they compete with one another, replicate, And you could then perform experiments to set up conditions and investigate how selection is working. I'll just sort of show you a quick stop motion of what it looks like in a dish. Here's a population of organisms. Here the color coding just shows different kinds, particularly their fitness levels as they evolve new abilities. And you can sort of see as the bright, new, more highly fit arises, it takes over and spreads in the population very quickly. So you can use this for all sorts of things. Here's one of our favorite examples. This is where we use the system to investigate how it is that the evolutionary process can produce complexity, okay? In particular, complex functional features. And Darwin had an explanation of this in a very general, abstract way, and he was right in the way that he did it. But he said, you know, just by the nature of evolutionary history, we'd never have a chance. What would be best would be if we didn't just have to have comparative evidence here, but if we could actually run experiments and do this. And too bad we could never do that. But now we are in a position to do it. And what this did was sort of, for the first time, go through and systematically look at every mutation that happens from essentially an organism that can do nothing but replicate to something that perform a very complicated function. And we're able to see at every step along the way how it is that it's essentially taking small advantageous properties, using them, modifying them, dropping them, up to the point where you get something that's very complex. And you can, because we keep track of everything, we have a complete evolutionary history. And so you can work your way back and see how it is that was produced in as fine a grain as the way as you want. So this was something that really for the first time let us do an experimental investigation of something that I think was not surprising for evolutionary biologists, but it was a wonderful confirmation of something in a kind of richness of detail that wasn't possible before. The other thing that was kind of nice about this was that it allowed us to sort of show how it is that you can get a functional kind of complexity and a very, very unlikely functional complexity in a completely Darwinian natural process. And this turned out to be something was a direct refutation of the claim that the intelligent design creationists had made, which was that you can't in principle get an irreducibly complex or a functionally complex system. And that evolution can't do it, nor can any natural process do it. This is the key argument for why it is that you need to have supernatural intervention. This showed in as direct a way as possible that in fact it can do it and you can watch it happen. And here's just an example of sort of how you can see what's going on as you get the stepwise improvement over time. You can also sort of see how it is that evolution is incorporating information from the environment. This is just sort of an information theoretic heat map of the entropy of the system. I'm just going to go through a couple of the examples because I think someone has said, hey, what are some of the highlights? These are just some of the fun examples of using this system that we've done. This was one where the investigation was how it is that you could evolve the ability to extract information from your environment and use that to better get some resource. And in this case, it was just phototaxis, the idea that you'd have something that was brighter in one spot and you use the gradient of information to move towards it. So here we wanted to have a question about how evolution could essentially build a brain, evolve a brain that could process information and then move itself towards it, right, to get the reward of that move. So we initially did this in a virtual environment. And what you're seeing on top is the gradient and some pathways up that gradient. The bottom left is, or middle, is sort of a sequence how the evolutionary trajectory worked over time and the strategies that were used. And the bottom right, you can sort of see how it is that eventually they got to be very good and just work their way right up the peak, right? They could just get right to it. The other thing that we could then do is what's important for thinking about this really in the biological way I was talking about, you want to think of cognition as something that's in organisms, right? Cognition is embodied. And so some of the work we've done is doing this where we put it into robots. And that's the case in this case where we essentially downloaded the evolved brain into this little robot and then were able to watch it as it did the behavior that had been evolved. Here we have another one, from another of my graduate students, where we're looking at the evolution of associative memory use and learning. This was something where there was a pathway with signposts, and the idea was, could you evolve the ability to recognize information in the environment, including ones that would sort of tell you what to do, and essentially learn to follow a path to a reward, really rather complicated path, and avoid the poison. And this is an evolved brain that's been able to do that. It's evolved the ability to learn to associate a signpost with what you should do, turn right or turn left, okay, and how to follow a path in that case. It's learned how to do that, it's evolved. And then here is an example of the same kind of thing, but this is a little robot where we downloaded, not that one, but a different one. In this case, what it had to do was see if it could evolve the ability to extract information and then use a limited movement set to move itself around, in this case, towards the area of the resource, in this case, light. And what you did was see it as it moved itself first randomly one place, that's not any good. It realizes that it's getting worse. It tries a different place, it goes off there, still not any good, tries a different one. And then, oh, here it is. So you keep going towards it. Basically, it evolved a brain that could navigate with information extracted from the environment in this kind of a way. The last thing, of course, would be, could we do this to investigate curiosity? This is a current project where we're doing just that, trying to see how it is that you could evolve and under what conditions you would involve inquisitive behavior. This was something where it was supposed to be a two-part one, one digital and one where we actually, with a colleague, we were going to go and study hyenas in Africa. The pandemic scuttled that. So curious hyenas will have to wait for another day, but we can go ahead with a digital one. So this is a project that's going on now. The last part is now thinking not of curiosity as an instinct, but thinking of it as a virtue. Okay, and here I'm going to go through rather quickly to make sure that that you get at least some of the parts. The very first paper that I ever gave, it was actually while I was still a graduate student here, was on what I called moral Darwinism. It was an analysis of Darwin's argument in The Descent of Man about how it is that the moral sense can arise in a robust way through an evolutionary process. I think he thought of it as an instinct, right, in the same way that he's talking about an instinct for knowledge. Okay? So that's the connection that I want to make here, that this is something where you can have something I think is reasonably called, right, a virtuous disposition that gets both of those elements in there. We ought to behave like this if we want to know something, right? We ought to do this, indeed, even to become good at sharing. Another one of the experiments that we did, another graduate student, was using our system to test things about how evolution could produce cooperative behavior. And you could watch how it is that they would go from being totally selfish to being generous towards others, and essentially the evolution of that in the system. It fit with something that already was known theoretically, but here we could do it experimentally. Now quickly to sort of the virtue theoretic stuff that provides the framework from this. Here's Aristotle, of course, right? Virtues as dispositions, settled dispositions. He gives an analysis where you think of these in relationship to the end, right? The human telos, and that what it is for us to be virtuous in this sense is to actualize our human potential. And he's thinking about us as rational animals. Okay, so that's part of what it means for him to do this. What do you get out of this? You get eudaimonia, you get human flourishing. I'll credit Jennifer Whiting on this. I had a whole seminar with her on eudaimonia. Right? So this gives you a way of thinking about what the virtues are for a human being. And then he talks about how it is that you can learn this from the practically wise and so on. So that's in a very general sense. Here he's talking about the virtues for us as human beings. Okay? But I think focusing it a little narrower is useful. So here's McIntyre, where he's talking about what virtue is, right? And he talks about this in relationship to the exercises of those qualities that enable us to achieve goods that are internal to practices, a lack of which effectively prevents us from achieving such goods. But here he's talking about practices, and he mentions various things, but he doesn't really go that much into practices. But I think he ought to have. He certainly knew that that was a good place to look. And basically what I've done in my approach here is to say, let's think about practices in terms of disciplinary practices, vocational practices. And so that's my analysis of science, right? It's a vocational practice. And I use the term vocation rather than discipline because I think it really has the moral content of it. We're called to this, right? There's a motivational notion of it being a thing that has normative content. Okay. So here's the equivalent. Here's my vocational virtue theory, where we think about this in terms of the disciplinary or the vocational subsets. Now, not all of human practice, but now particular ones, such as science, right? That's one example. So you're thinking about the scientific mindset, okay? And then you would ask, well, what's the telos of science or the telos of this vocation? And for science, it's discovering true things about the world. That's the basic thing we're trying to do. What's flourishing going to be? In the vocational sense, it's going to be, in this case, a flourishing research culture. We'll be better as scientists. We'll do better at achieving our ends. There's a larger notion, because this fits within virtue theory broadly. So in the end, it still has to fit in with other vocations to get human flourishing. But narrowly speaking, we have a much more definable notion about this. That then gives us a way to analyze what it is to have vocational virtues. What are the character dispositions we ought to cultivate in order to be better in our vocation, in this case, as scientists? And then I think this then has implications for how it is that you justify, evaluate methods, okay? Well, why should we do this, right? Why should we have this kind of protocol, this kind of statistics and so on, this type of methodology? I'd say the justification for this winds up coming in relationship to the telos and so on. Now, this is part of sort of a broad vocational virtues project. Here, I'm just really focusing on science, but I've also done things where we're thinking about this under other contexts. So what are the engineering virtues? What are the healing medical virtues and so on? We've even started to do one now on the humanities virtues, the scholarly virtues and so on. But I'm going to stick my focus here on this because that's where I have the most developed view and the most evidential basis. We have some evidential basis for the others as well. And I'll leave that aside. Here, I'm just going to talk about the scientific notion. So the initial work on this was just theoretical. As an advocate for thinking about this philosophically, what would one expect? This is my armchair philosophy, right? So providing a philosophical account of what a virtue theoretic philosophy of science ought to be like. Tracing that historically, so that's the H part of this, asking, are there roots of this? And indeed, I think there are. So that's sort of the HBS component. But the thing that was sort of missing from this, which I then felt I needed to do more of, was how to get some social science into it, to say there's some empirical basis for this. Because there's nothing else that sort of came out of my time at Pitt. It's that we ought to do science by knowing it really well. And I always felt that we shouldn't just study it, that we needed to actually do it, which is why I wound up doing evolutionary biology. And I felt here I needed to do some social science. So in this case, then, done this long study, which I won't be able to talk about now, but I would love to talk about because we're at the end of an 8-year run of doing this, and we're not ready to do the final thing, where we asked a random sample of 1,000 plus scientists what they thought of as the important traits to do science with excellence. Okay. And so I have a data set of exemplary scientists, early career scientists with 500 hours of interviews. I'd love to tell you about that, but basically what that did was to test the intuitions that I had to say that this ought to be something that scientists should care about, to see then if they do. The third component of this is they're practical. Let's see if we can get this into the practical wisdom sphere and to use it to make us better scientists. So I also have projects where we've done this for responsible conduct of research and so on. So I'll just say a little bit about this. Some others have already talked about virtue. Chapin talked about this, right? He talked about this early on with regard to how it is in Victorian times. It was trust that you got by virtue of knowing that others are trustworthy. And he analyzed this in relationship to the gentleman of the time. And so, that's great for a limited notion, but I don't think that's the fundamental notion that we want to. So this is to me just a small point. We should trust and think of virtues much more broadly than that narrow historical sense. But there are historical components to this. Here's one example, right? Here's Huxley talking about an attitude. Sit down before fact like a little child. Be prepared to give up every preconceived notion. Follow humbly wherever and to wherever abysses nature leads you. This is this idea of intellectual humility and what came up in our study, the idea of humility to evidence, right? As a character trait that's fundamental to what it is to be a scientist, right? You have to humble yourself before the evidence. And if you don't have that mindset, you're not really going to do science very well. So there are lots of cases that you can find in the history of science, especially in the early part, where scientists are reflective about sort of their mindset. And this is just one example. I think some philosophers of science have also thought about this. So here's Lakatos. Actually, part of my book was sort of an attempt to sort of develop what I think Lakatos was hinting at, where he's talking about what's behind testing, right? It comes from the best of human qualities, courage and modesty, the modesty being the humility to evidence again, the courage to put something boldly forward and so on. And that's an attitude you ought to have if you're going to do this well. So again, I think this is something where there are places where philosophers already thought about this. And so my suggestion is, there's a lot of room here to investigate this further. All of these dispositional traits can be things that we should and ought to investigate, not just the nature of theory, but also the nature of the theorizers, the investigators. So that's the scientific character. So that's my recommendation, right? That we not just think of philosophy of science in the way we've focused on, but that we expand it to include these other sorts of things about the nature of the scientists themselves as practitioners. What are the traits that they ought to develop and cultivate and hone, thinking of ourselves as instruments that can be calibrated. We could be better disposed to do things in a certain way. We ought to be investigating these things as philosophers of science, right? I think we've started to a bit, but my suggestion is we need to do more of that. Part of it is that it's hard. When I started doing this, the thing I did was interview scientists informally and to work with scientists. It was nice to do the study. I'd been waiting to get funding to do that so I could do it in a more systematic way. It's hard to get the data for this. We can't just rely on our own intuitions. You have to do the work. But I think that's available and that we as philosophers of science ought to be doing this. So what are some of them? Here's a quick summary of what I did, right? Starting theoretically, doing informal interviews, asking open-ended questions, doing a pilot study, asking, so we did this, and here's just a word cloud of what came out of that. Honesty turns out to be up the top, curiosity in second. I'm not going to go into the details of this now. This is very word cloudy, but we have now very precise, and we're doing the confirmatory factor analysis to see how these all fit together and so on. But there is a coherent, we have found, set of values that are really broadly held in a unified way. This then leads us to what we can do in a practical way for responsible conduct. I think this allows us to give a framework for improving the way that's done, rather than just compliance with rules. Some of that's important, of course, but I think thinking about this in terms of the character virtues gives you a new way. So over the last 8 or 10 years at the Beacon Center, we developed a curriculum based upon this, which we implemented as our approach. And then I now have a new NSF grant that's specifically for expanding this for the university. Here's just an example of this. Traditionally, when you're talking about don't be a data fabricator, right? You're giving perhaps duty-based or utilitarian reasons for doing this, or don't do it because you're getting caught. Typically, scientists feel of this as something that's coming in from without, right? It's the ethics police coming in as something that's foreign to it. But from this notion, you think about not doing this because it's inimical to the very telos that you're after, right? Data fabrication undermines the very notion of finding out something about the world. So you build that into training. I think this also has implications for science education. So part of what I've been doing is start to do that as well. We ought to be cultivating the scientific mindset in addition to just getting content across, in addition to getting methods across. Values, virtues ought to be part of what we do. So I'm just going to name some projects that I've done now, and I'd be happy to tell you more about them. Vita Ed project, which I showed you a little bit about just what it looks like, is our digital evolution model system. But the Ed version is what I developed specifically to be used for teaching about evolution, but also teaching about the nature of science, because it becomes a model system that lets you have the ability to do those practices explicitly. We put on faculty development workshops around the world for this. These are some of the people who've done this. And then recently, I'm excited about this one because we just finished it last week. We now have a 12-part video series that essentially shows faculty how to make use of the system for their classes. And then I started, because reviewers were saying, boy, well, that's great for undergraduates and graduate students, but you should do something for younger ones too. So this is now a system that we're developing that's specifically for the K-12. That's essentially, again, a model system where you get to play and figure out how it is that the salmon evolve in this system. So this is a project in process. This is what I mentioned before, our new NSF one, virtue-based education for responsibility and integrity to increase excellence in STEM. I'm especially proud of that acronym. I worked on that one for a long time. So this is an NSF institutional transformation project. Basically, it takes what we did in the Beacon Center and the evidence that we got from that, and now it expands it across the university and so on. I'm also now, and this is one of my things as president of Sigma Psi, Scientific Research Honor Society, is that we're trying to expand this as a national model and to use the chapter-based system to do that as well for mentoring, to get people who might not have thought of themselves as scientists to identify for what that means and really to be able to expand the scientific mindset in that kind of way. So this was from the conference we did this last year. So let me just end with this. To go back historically again, Frances Wright, talking about science, she says, as the surest guide to virtue. The sciences, she says, has ever been the surest guide to virtue because demanding calm observation, obtaining all their results by means of dispassionate investigation, they bring into action our noblest faculty, the judgment, and submit the imagination to its guidance. Dispose us by the previous accurate observations of things to an equally accurate observation of ourselves, okay? And confirming us in the habit of tracing effects to causes in the world without, prepare us to follow attentively the train of occurrences in the world within, okay? And there I think we have many of the elements here of this type of approach and its value, not just for philosophy of science, but really for development of understanding of the mind and ourselves as well. All right, I'm going to thank, because this is the result of many different projects and many people. These are collaborators, a couple faculty and my graduate students and postdocs from the Evolving Intelligence Project. These are ones over the years from my Active Lens educational research project with Avita Ed. This is the group, my collaborators for the Scientific Virtues National Survey. And then here's my current group for the Verities Project and the Scientific Virtues RCR training. And then some of my collaborators, this is from our Beacon Center. In the end, we've had now currently over 500 participants in this. So there's a huge range of work that we do, but these are some of my things. So all of these are to be thanked. And then finally, all of these roots for me go back to here. So not just Wes and Wilfred and Herb, but really all the professors that I had here. And I wish I could have said something about all of them because they all had roots in this. So I take this opportunity to thank them. And I thank you for your attention.
45 seconds break. If some of you need a short minute. And then we'll reconvene in less than a minute. I know. You got it, right?
And if you don't mind, the online audience, if you could just repeat for a quick.
If there's a question from here, sure thing.
Yeah.
Yep.
All right, let's get started. Go for it, please.
Thanks, Rob. So if I were to be a little cynical, I suppose, I would look at the children's version and point out that the biggest thing at the top part of that screen was $1.
The biggest at the top of which?
Was the money.
On top of which screen?
The children's version of the Salmon program.
Oh,
right.
For the
biggest
Salmon.
letters were for money, right, on the top of it. And that leads me to also sort of wonder to what extent, given that, as you say, scientists have always sort of been very explicit about cultivating these sorts of virtues, to what extent that is actually evidence against kind of instinct for this, rather than an attempt to enculturate people into something that goes against what other instincts or what other cultural pressures are there. So I'm just interested in your comment, sort of the tension between the idea that there's some instinct here, and the idea that you need to keep reinforcing and educating people.
Yeah, absolutely. So the claim here is not, of course, that this is the only instinct that we have, right? Biology gives us multiple dispositions, okay? And the idea here is let's hone in on this one, which is relevant specifically to becoming knowledge acquirers and so on. I don't think of this as by itself being enough to make it science, right? You need to have it systematized to be science and so on. But I think it has to have a basis in this, and that we can tell and give an account of why it is that it's something you should do, right? So that's the normative aspect of this. The dollar figures that you saw on that one and so on are to point to the fact that we have other motivations as well, right? And the way it figures in the game there is actually as a way of being part of the decision making that you have to do. It's a tower-based game where you have to make use of interventions in the world, and you see what happens. You use the money then to buy a dam or to buy a fish ladder or something of that sort. So here's the example then, right? So you think, well, are we perhaps swayed by money, right? Some other sorts of competing notions. So the analysis here would be to say, that's how we can make sense of this idea of conflict of interest. Okay, this is meant to be a normative account. It's obviously right, that people, scientists, are drawn in different ways, right? But this is meant to be something to say, this lets us evaluate what we're doing and point out you ought not to do that. Okay, this would be an example of something, right? If you're drawn to the riches, right, as opposed to being drawn to the finding out about the world, okay, then you're doing something that's not central to being a scientist. Okay? It could be other kinds of virtues or other kinds of vocations where you have that as well, and you have to balance them. But here, it lets us say, here's why you ought not do that as a scientist. This is meant to be something that's regulative then, not just descriptive. Okay, because clearly scientists can say all sorts of things. We didn't ask them, how do you actually, do scientists actually do these things? That's a descriptive question. We asked them specifically about, should you, what ought you to? So that's what this is meant to be. And then it gives you a way to critique what scientists do if they're doing things that are departing from it. And it also gives us a way to do what we need to do, because it's not all instinctual, to cultivate it. That's what we need to do as systematizers, to say, this would make us do us better. We ought to change our methods. We ought to teach better, so on. So it's meant to then be something that can help us improve.
Yeah, go ahead.
Well, so good. So, I mean, 2 bits, right? So the money in that game in particular is a resource rather than a target.
Correct.
Right? Okay, that helps. The other is just coming back to what exactly is this? I mean, let me grant you that there's some sort of truth-directed instinct here, but you were clear to say it was more like Simon, like satisfies.
Yes.
Right? And you might think that actually people have a pretty good instinct for being good enough without really pushing to the level of understanding that's knowledge for its own sake. So why would we have this further drive to knowledge for its own sake if in fact what's good enough is way short of just gathering facts?
Yeah, so for any particular question, that's always a reasonable one to ask, right? Have we done enough, right? We don't have a way of knowing when to stop the computer, right? You can't predict that, right? But you've got to make some decision about how much you're going to invest before you say, okay, we're going to stop. And I think that's a reasonable thing to do with regard to any inferential process. Okay, ask ourselves, when is it that, given the nature of our question and the possible things that could happen, it's reasonable to say we have enough. Okay, but I think this sort of gives us a framework for saying something about that, right? We're not looking for God's eye knowledge here. We're looking for a human knowledge that's then reasonable, right? Justifiable, warrantable. And that, I think, essentially provides us with an avenue for starting to make these judgments and saying, well, we ought to be explicit about them. Okay, here's what we're going for. Now let's figure out, right, is this worth more or less investment? Now, from our point of view as philosophers of science, we're invested in really systematizing things at a rigorous level. So I think we have a lot of motivation to do that sort of thing. Sometimes the scientists think we go too far, okay? And for real practical purposes, maybe we do sometimes. Other times I'd say, no, we're actually helping them be better scientists by pointing these things out. So it gives a role for us as philosophers of science to essentially give some guidance in a principled way about what they might consider doing.
Thank you, Vince. I wanted to invite you to say a bit more about the scientific virtues, and in particular to say a little bit about how the science project differs from the engineering project. Because I'm very interested in biologists who adopt what Phil Pollock called the engineering ideal, like Jacques Lowe. So we just finished editing a book called Nature Remade about engineering ideals in biology. So what's the difference between virtues for engineers and virtues for scientists? And can you have people that sort of fall in between, or Tell us more about
Yeah, so that's a great question. And this actually became a methodological question we had to deal with when we're doing the study. But let me just talk about it theoretically first, right? So the vocational virtue approach says, let's think first of all about what the telos of this vocation is, okay? Because that's going to be the ruling standard against which you're going to judge what counts as a virtue, right? Because this is a trait that will make it more likely that you'll achieve your goal. Okay? And the vices would be the ones that make it less likely. So you move in that kind of way. Okay. But it requires that you try to be as precise as you can about what the goal of that vocation is. Okay. I think theoretically there's a difference in the telos, the scientist, the research scientist, from the engineer. Okay. The research scientist says, I want to find out what's true about the world. Okay. The engineer says, I want to make something in the world that never was before. Okay. I want to design something useful and new and so on. And their standards of judgment are quite different. Beacon, our center, was actually a combination of research scientists and engineers. So that was actually part of what was interesting, to combine these research cultures in a way so that we could work together, because we could regularly see that difference in mindset actually would lead them to behave differently and to not care about something that the others did. And if you could work together, you've got to figure out how to do that. So that's the framework of this. For the study, empirically, we could show that scientists really do have a very surprisingly unified notion of this. We were only able to do a focus group with engineers, so I don't have a full seat for that, but I think there's some evidence there to say that they do have their own interests that are different. But you're quite right, they're intermittent ones, right, or intervening ones, right, that could be hybrids. So you can have bioengineers, right? And so that then is something where you've got to figure out, okay, well, what is it we're actually doing specifically in this project, rather than sort of thinking we could just sort of switch hats and that kind of thing. So it actually turns out to be really interesting for interdisciplinary research. And one of my colleagues, Michael O'Rourke, another philosopher, science at Michigan State, would collaborate on this. He does work specifically on interdisciplinarity. And this is one of those sorts of issues, how you get collaboration between individuals who have different research interests, right? Different vocational interests. And I think there's interesting room there for us to do some work as philosophers.
Thank you for this incredibly fascinating talk. So for a while now, I've been interested in the question of how we manage to ask a question. This is not a top-down, but rather a bottom-up issue. The problem is how we evolve to be able to problematize anything, basically. And so I'm not very much convinced that the instinct talk is a good road to take. Perhaps the notion of curiosity is better, but the curiosity literature mixes two things. Especially, they talk a lot about our dealing, or other animals dealing with novelty.
Yes.
This is not about novelty. The opposite rather is true. So, for example, you can have rain every 2 weeks, and suddenly at some point, theoretically speaking, at some point, somebody or some creature asked for the first time what is going on up there. Actually, that there is this water going down. So, do you know of any models, let's say, of this incredible, basically, capacity of problematizing our environment?
So I was told I was supposed to repeat the question. I've forgotten to do that at every time before this, and so let me try to do that now. So the question has to do with how it is that one can get off the ground the idea of questioning, right, and so on, when that doesn't seem that instinct by itself is sufficiently rich to be able to capture that. It seems like it's another notion that what animals are doing is somehow not quite there yet, and so on. So which is a great question, because that's the general question that I'm posing, right? How do we get from there to here okay? So the way that you framed it is something where I would say immediately, okay, posing of a question, right? That's already putting you in the realm of systematizing in language, right? So it's a notion of that sort. But if you think of it in not that way, as a quizzical, right? If you think of that as the posing of a question, okay, then I think we begin to have a toehold, okay, where you could have something where I think the way it works is a disposition that begins to see something that's unexpected, okay, because I think this is the basis then for how the motivation for an inference goes, right? You have an expectation that you've developed, and then you see an anomaly. You see something that's a departure from what you would predict. Right? That then elicits what I would say is essentially the instinctual right? Because it's a puzzlement, right? And I think that's the low level notion of a question, right? It's sort of like, and I think that you can investigate that even in animals and so on, where you present them. That's part of what we were going to do with the hyena case, right? We were going to do a protocol where we would present them with things that would be essentially puzzles, and to investigate that inquisitive behavior into that. I think you can do this in other systems too, and partly what we're trying to do in the experimental digital system is to create something where obviously there's not the feeling, but there is the move to investigate when an anomaly arises, right? Here's something new, that doesn't fit with my prediction, okay, let me investigate. Okay. So I think that's, I would say, is at least the avenue for being able to pose those sorts of questions.
Just a quick follow-up.
No, we have 8 minutes.
I will email you.
Yes.
David, go for it.
Sure. I'm interested how much, what you think about how transferable what counters the scientific virtues are across different scientific communities. I mean, would I expect to see, or do I have good reason to see the same kind of virtues in theoretical physics as I would in
Yes.
biology?
Yes, yeah, a great question. That's one of our research questions for the national study, right? We wanted to specifically see, first of all, whether there's something generally true about the scientific community, and then whether there might be a disciplinary difference and so on. So I really ought to ask what your hypothesis would be with regard to that. Would you expect there to be a difference between the?
My guess is there'd probably be a core overlap that covers a lot of the really important things. But then there are going to be sort of commonalities. I mean, think things about, appropriate use of various formal tools that are going to be widespread enough that you could have other mathematized bits of physics and chemistry with them, but which wouldn't necessarily have analogs in field ecology or something. But I'm just guessing. That would be my hypothesis.
Yeah. So this is good, because of course what you did was immediately think of this at different levels of specificity, right? And that's what I would predict as well, right? That there's something that we do and ought to do, right, as scientists, right? Whatever the field would be, because we have a common interest, right? Finding out things about the natural world. Okay, so there's going to be something that we should be expected to share. Okay. And so in that case, I would say it'd be pretty surprising if the physicists and the biologists differed on those things, because they share something like that. Now, I've got to say that that was a question that we posed, but we have not yet done that analysis of the data. That's something that's coming up within the next month or two, as we're right at the point of being able to do that. So that will be something we'll be able to see whether there are some disciplinary differences. I can't give you the answer now, but probably in 2 months I'll be able to. But I think you're exactly right that the level of detail of the differences is likely to not be at this general level of virtue, but really more at the level of sort of specificity of methods. Okay, and I'm going to give you an example. One of the virtues that comes out as being important across the board is the idea of meticulousness. Okay, and the way that I talk about this in Seek for Truth in general is it has this idea of of being, rigorous and quantitative and so on. It shows up in different ways, okay? But the idea is, you've got to cross your T's and dot your I's and make sure that you don't have any contaminant. I mean, all these sorts of things. And I think that that's the level at which there's going to be differences, right? How do you put meticulousness properly into practice as a theoretical physicist compared to a field biologist, for example? But I think then, again, it puts us in a position to be able to give an account of a normative account of why it is that we ought to do things, and also a judgment of how to appropriately do it depending upon your area of study.
5 minutes into question. Keep in mind. Katie.
So I'm wondering how you think about the relationship between this virtue theoretic account of the scientists in relation to other accounts or theories of the scientists. And I think particularly Heather Douglas is here this year as a senior fellow, and she's given arguments about the responsibilities of scientists that go beyond just doing science well. So could you say a little bit more about?
Absolutely. Yeah. So the part of what I think of as the value of this framework is that it provides an ethical, and here I'll focus on the ethics because I think that part of her issue specifically has to do with these kinds of ethical responsibilities and so on. But I would say generally our normative responsibilities, part of what's useful about this has to do with the way that you combine epistemic and ethical values together. So that's part of the goal here. But what about going beyond science? Okay, so that's the notion here of what I just gestured towards, that these are focused values for your role as a scientist, okay? Or your role as an engineer, right? Or your role as a physician, and so on. So it limits the scope of this initially to achieving what your bounded responsibilities are, right? The bounded virtues and so on. And as I said, the vocational notion is flourishing of that. But the broader notion then still fits in virtue theory generally, right? Which is for human flourishing, okay? And that's then the way that you can use this to bring in these other things, right? We as scientists, this is why we shouldn't be scientistic, right? We have a limited scope, an important scope, but a limited scope of what we ought to do. And in the end, all these different vocational projects have to combine to think about human flourishing generally and what it is that we bring to it and what it is that we need to stay away from and so on. And this then is one of those examples where what we do needs to be thought of in relationship to the broader social picture. So I think this actually provides a nice way to evaluate what scientists do and what they ought to do, but also how they need to then work with other vocations and so on for the more general social good.
Yeah, I think I think that you partly already responded to my first question that was about the fact that the telos in Aristotle is also related to the realization of the common good for a community. Many in Aristotle is a little community of the story of the best, but it has to always be integrated in a. And then we said that this decision. The second answer is if you can articulate a little bit about vocational virtues in medical sciences. I have told that you have analyzed also the part, because the issue of professionalism, for example, is very debated in medical sciences, and sometimes it is confused with the sort of individual sacrifice.
Of individual what?
Individual sacrifice for the humanity. The vocation in health professionals and medical professions is very late.
So I'm not sure about are you pointing to a tension there between sort of what you ought to do versus those who go into it because the salary is large and so on. This is equivalent to the issue of the dollar sign. Is that the notion? Some things along that line. Okay, so I'll respond to that in a similar way, but with this example. So again, you think what's the telos of the physician, the health professional. And there, again, first from a theoretical point of view, but then from the focus groups that we've done, there the idea is therapy, right? You want your goal is to help someone improve their health, right? That's the goal, right? You're there for that purpose. Now, that's different from the research medical scientist, right? So here I'm talking about the clinician, right? So we're talking about the medical virtues. Here I'm talking about those of the practitioner, the clinician, and so on. And there I think you can then have a similar sort of analysis, right? The central goal for this is to do the things that will make you better at that. So one of the virtues that comes out in this has to do with empathy, right? So that's an important theoretical virtue, medical virtue. That's not so important in the engineering case, for example, but it is important here. But you're right, as in every other case, we're human beings. We have conflicts of interest. We also care about, so, but this gives you a way to give some oomph to the idea that this is what you ought to do. And part of what it does, I think, is that it actually does this from an internal notion, right? This is actually part of what you signed on to. This is what you're called to do, right? You're called to this mission, right? And maybe you don't realize that these are counter to that, or at least in tension with it. And again, it provides a way for us to start to be evaluative and then critical, and then hopefully, change policy, improve policies with regard to incentives and so on, to make us better in that role. So thanks for your question. Yeah.
All right, it's time to stop. But before we stop, we'll give for the center for the coming rainy days. Thank you very much.
So next week.
We'll talk on